So good morning. I'm actually going to take a different perspective, and I'm going to try and get you all to zoom out and see the big picture, the bigger picture. I'm actually no longer in active research, but my position with Nvidia affords me the fantastic opportunity to both advise on and witness just a vast number and breadth of applications that deep learning is impacting. I've lived with and therefore understand the assistance afforded to many using the power of information technology and now artificial intelligence. I've also studied just enough astrophysics to really understand what NASA calls the orbital perspective. So it's this big picture that I was talking about. To be able to see the planet as this big, huge connected ecosystem that's yet this fragile speck in a vast existence. And my passion for this field may possibly stem from my mother, who joined the European Space Agency at the young age of 22, but it's also because I know the combination of physics and artificial intelligence is a really powerful one. Science, at the very least, knows no geographical boundaries, and it's very, very able to assist us, in particular with deep learning. And I talk to many people. I go to a lot of different events. People who perhaps don't yet have the specialised knowledge in this field. So to those in the audience, which obviously will be the majority, forgive me for taking this high-level approach. And this, as well as myself working for Nvidia, is me in my literal second life. I don't know if anybody's familiar with this virtual world. I'm actually stood in my Second Life's charity office. We don't have actual infrastructure. We use VR. At least for what I do, and this also goes for Nvidia. I don't need an office. Tech now means that we actually don't need offices when we're talking about global work, global impact. Virtual reality and augmented reality is actually offering incredible assistance to billions around the planet. And this is actually powered by AI and, of course, GPUs. This is quite an old picture, and it's not really come up too well on there. I don't know if you can see the avatar dressed in white. That's a friend of mine called Louise. In front of her is Max, her virtual guide dog. In Second Life, and now coming into real life, there are all sorts of assistant technologies. And Max basically reads text chat out loud, and this is using deep learning techniques to assist people who are blind or visually impaired in real life, like Louise. Louise lives in Pennsylvania. This is her avatar, and that's her virtual reality guide dog. Of course, in Second Life, we can all fly too, but we've yet to get there. So my spare time has me regularly conversing with all sorts of people, including Maasai warriors. This is Jackson. And incidentally, altruism is the real key to happiness. I can definitely stand here and tell you that. The Dalai Lama told me that in Manchester in, I think it was 2012. And Mark Zuckerberg, Larry Page, et al. Have thankfully all ran with this knowledge too. They're proliferating hyperscale deep learning. Deep learning backends for the millions of us who possibly will never really understand the concept, but hopefully will understand the impact that it actually brings. Jackson recently graduated from primary school. His English is fairly mediocre, but he speaks it way better than I speak Ma. And luckily, perhaps lazily, I can use Google to translate via recurrent neural networks. And it helps me to converse in a multitude of languages. Jackson, of course, does have his he's actually now got 3 mobile phones because of batteries and all the rest of it. But he has access to this kind of technology now. And he actually loves it. He's really into tech, as well as sort of herding goats and looking after the cows, etc. So to really understand deep learning, you need to first understand shallow learning. And taking a medical example, this is Brendan Frey, University of Toronto, and now Deep Genomics. Earlier this summer, he started a company that began probably 15 years ago due to personal reasons. Shallow learning is looking for DNA mutations that commonly occur in patients with a disease, but mutations occur in clusters. And the true causal one can be buried in clusters of non-causal mutations. And identifying the causal process is important to figure out how to treat disease by reverse engineering the process, by gene editing. Specifically, it's the way proteins bind to DNA. Frey's deep bind algorithm computes whether a protein would bind to a sequence and influence cellular processes. It does this using deep learning, and it essentially allows a personal medical diagnosis engine that's able to identify therapeutic treatments, etc. And it also improves the more it actually operates. So it's similar to ourselves. The more we learn, the better we get, the wiser we get. Genomics is the next big frontier for deep learning. So, pattern recognition, essentially pattern recognition, and it's through mathematical feature representation in vector form of objects, scenes, situations, but this is subtle pattern recognition. Patterns we're not even aware of, patterns we couldn't possibly see. We're not built to work our way through terabytes and terabytes of data. Terabytes of data, for example, coming from a financial trading floor or coming from the archives of an fMRI machine. It's also lots and lots of inference, constant inference. Right now, my mind's trying to determine the next word. You're trying to determine the next word. You're making these constant inferences. We are walking, talking inference machines. So this has a lot to do with deep learning systems. And deep learning, like the human mind, in the sense that they are similar because they work, but we don't really fully know how yet. And there is lots and lots of research that's trying to open up this black box. Things like network inversion tactics that Oxford's VGG group are doing. There's just the actual research and the pace of this field is really phenomenal, and it's really exciting to actually be a part of all this and see it happening. And it's purely mathematics, really. It's number crunching through hierarchies of layers that do closely match the first 3 or 4, at least, in our own visual cortex. Neuroscientists, of course, will grimace at that, but there are similarities. That is working, that's good. Okay. I pinched this GIF from the New York Times, who recently published again the theoretical neuroscientist, Kenneth Miller. I think it was last month that they put this article out, and it was about the whole uploading our mind issue. Saying how, Kenneth was saying how far we are from that capability, but not ruling it out. If you actually take, for example, we heard a lot about iris recognition yesterday from John. If you actually take the complexity of our retina, for example, it's not just an image that we see. Our eyes are actually in constant motion from ocular microtremors. And our brain is constantly integrating the output of the eye as it's moving around into the image that you actually see. And we're doing this in a massively parallel way. It's massive connectomics, massive scale connectomics, massive complexity. And if you take, for example, the weights in deep learning, within our own synapses, we know these weights are doing a whole lot more than this single computation that we abstract to in neural network computation, this x1 times weight 1. But we're learning, and we're learning very quickly about deep learning. So I've pinched this GIF from Andrei Karpathy at Stanford. He's really excellent at teaching this subject. He's also responsible for our only human reference of 5.1% accuracy. He literally taught himself the 1,000 different groups in the ImageNet dataset. So what we're doing is we feed in a raw image. For example, here a wolf or a toad, and it's represented as a three-dimensional grid. So, for example, 256 by 256 by 3, the 3 being full colour RGB. And without going into too much of the detail, I'm sure most people understand the actual basics of it. You're basically taking small filters and sliding them spatially over the image. This is a convolutional neural network. This is the different filters get excited over different features in the image. Some might respond strongly when they see horizontal edges. Some may be for the colour red. The first column in this GIF is the activations. But what's happening in every other column after that is just a repeat process of convolutions, where all the other columns are just the exact same operation, but it's the filters being applied to the previous column's responses, and gradually detecting more and more complex visual patterns, until obviously the last set would be something like a softmax, and it's making the prediction of exactly whether it is a wolf or it's a toad. Very trivial example here. But what the filters are looking for, we don't really know. This is the ongoing research, the ongoing learning that we have to do about deep learning. But it's literally simply learning representation of objects. And this can also be representation of the iris, representation of your actual face as opposed to the person sat next to you. It really is intricate, and we can also do this with sentiment. So I'll skip for the fact of time, but technically, in a convolutional neural network, we're expressing a function, the deep neural network, from image pixels to class probabilities, for example. So running through, and this, of course, is for a convolutional neural network, we're adding labeled images. With supervised learning, you start with a huge number of annotated images, and really huge, millions and millions, for example, are needed to get good accuracy. And essentially, we're feeding them into a blank canvas, an untrained neural net. And it's like a newborn baby. These are, of course, task-specific systems. So you predetermined what you actually want it to do. In this example, it's learning the difference between a cat, a dog, and a tree. Again, very trivial. But it's according to the data set. And it outputs probabilities of results, for example, 80% predictions that the image is actually being a dog. And it's really the repeating process that I need to emphasize to actually get the trained model and then to be able to move to the inference side. And I have to emphasize the repetition. It really is lots and lots of repetition. Supervision is necessary for, obviously, supervised learning. It's just rinse and repeat. In this particular situation, it wouldn't be advisable to use something like unsupervised. I mean, the poor child will probably fall off the table. But essentially, you have to have, for supervised learning, you need that person to pass the balls and lots of ping pong balls, i.e. data. So that is essentially supervised learning, a lot different. So switching to why now, it is because we now have, as Jane said, big data isn't so much news, but it's the fact that we have access to this big data, lots and lots of big data. And we also have, of course, I work for Nvidia, GPUs, and it really did make a big difference. And it's also moving the progress of the algorithms. We're still using very, very ancient algorithms. Backprop itself is based on the chain rule, and this is over 300 years old, the chain rule. But the actual improvements and the progress we can make with GPU power with all this data means that we can go to prototype, we can go to development a whole lot quicker. Jeff Hinton's team in 2012, but it was even before that in 2009, I think, that GPUs were first used with neural networks, when they realized that the GPUs that were originally used for pixels, for video gaming, this is where Nvidia started out, were actually a perfect match for the millions, trillions even, of floating point operations that are actually needed. So having the compute power and the big data, we can, and we are truly progressing. So they were essentially designed for, as I said, the same mathematical operations. And I do have to say here that Nvidia were completely taken by surprise. You know, this wasn't something that we planned. It just turned out that GPUs were a perfect match for this. And ever since that, we've actually been trying to control this and keep up, shall we say, with this epic pace. I've actually watched as major research labs have worked their way through Nvidia's entire range of GPUs. And we're doing tireless research with parallelization, with overlapping communications, for example. But also brute force is being used, and maybe brute force isn't the way to machine intelligence, but you know, we have to go through the brute force route and use as many GPUs as possible until we start to think a little bit more outside. But essentially GPUs are just great for teraflops, for bandwidth, and deep learning is definitely hungry for both. So what we needed to do was not just provide the actual hardware, we also needed to provide the software. And it was from researchers and from collaborators that we were working closely with, and it was those requests that we then started producing the actual software. So, so this deep learning platform that we devised has highly optimized libraries of deep learning primitives. We've developed network training tools. We have advanced system management features for when you're actually going to deploy, even at hyperscale now. The stack shows the different applications that sits on top of digits. I'll show you just a couple of slides in a minute on digits. And this is actually on top of the many open source deep learning frameworks that are available on top of QDNN, which again is open source. It's all freely available on our online ecosystem to help you in prototyping, in rapidly progressing this field. And of course, in the actual impact that it actually brings. So solutions for you, we don't just have the large-scale GPUs, we also do a lot of embedded work. As I said, I see a lot of different applications around the globe for this, and a lot of devices now need to be embedded. So Titanx, Tesla, we're also virtualizing all our GPUs and working with many partners for cloud applications. So I mentioned digits. Digits is essentially just a really great GUI. It's a complete pipeline for developing deep neural networks, for pulling in and processing data and configuring the network, either custom or out of the box. For true visualization, it allows you to watch and monitor the accuracy and the progress that you're actually making, visualize the layers, etc. But what we found literally within just a few months of releasing digits, researchers and collaborators came back to us and said we really need capability for multi-GPU. So it's already been upgraded to digits 2, which allows up to 4 cards at once. And again, you can control all the resources of the GPUs, all within this same GUI. The performances on this table are based on Nvidia's fork of Caffe with QDNN version 2. QDNN, as I said, the deep learning primitives, this works alongside the major frameworks. We are struggling to keep up with the pace of the field, but the frameworks will fill that void as we work towards it. It really is, again, quite unprecedented, the rate of progress. But what's happened is just over the space of this partial year alone, QDNN 4 is currently in beta, and we started the year at QDNN 1. So that's fairly unprecedented for software. But alongside digits and QDNN, and obviously the underlying CUDA language for working with GPUs, we've effectively doubled the performance of deep learning already. I'll skip through that for time, I think. So what we're doing this for is so that you, as researchers and industry using deep learning, can have impact on society, to contribute to DL's unreasonable effectiveness, to steal a quote of Jan LeCun, the director of Facebook's AI lab. Unreasonable effectiveness across many, many domains that I'm lucky enough to be a part of, using trained models or also researching unsupervised learning as well. And it's across every walk of life, in cars, on phones, in medical applications in particular. Obviously, we heard earlier on the actual breast cancer. My personal research was working with mitosis in breast cancer cells, and mitosis is effectively cell division, but it's now proven. My research was to actually prove the concept to my supervisor, who didn't believe that it could be done, but I had a fairly easy time of it because it had already been done. In 2013, IDSIA, the Swiss AI lab, were winning competitions to prove the fact that machines are able to find these intricate, tiny, it's feature recognition that could predict the actual possibility of something being untoward, of there being a problem. And what's important to state here, I think, and this obviously goes to John as well, that the intention for using deep learning, especially in medical, is to assist us, is to take some of that workload off the clinicians, the trained professionals. It's not to take the jobs, it's to assist them. A deep learning system doesn't care if it's been running for 36 hours. You know, a 12-hour shift is nothing to a deep learning system. If you can set that thing running while you're attending to your other patients, then I don't see the harm in this. We've already proven to a human acceptable level of accuracy that, for example, in mitosis in breast cancer cells, that deep learning systems can certainly help. Platforms like IBM Watson, of course, you know, they're doing a whole lot, but it is more to be assisting humans and to have the impact that we actually need. Artificial intelligence perhaps suggests replacing the human mind. I actually prefer intelligence augmentation, and perhaps we need to rework that byline that everybody's working with. So in 2009, Google Voice used Gaussian mixture models, which was the state-of-the-art in speech recognition for 30 plus years. In 2012, deep neural networks had revolutionized the field with discriminative training. And it allowed this renaissance, this R-renaissance, as Jürgen Schmidhuber of IDSIA calls it. And if you want an example of a hyperscale deep learning system in action, deployed at scale in a mobile device, just use Google Voice because it uses recurrent neural networks. The additional recurrent connections and memory cells basically allow memory. Our thoughts are persistence, as Christopher Olah says. We need to be able to remember data, and this is the reason that recurrent neural networks were actually brought in. But interestingly enough, from that, naturally, as Schmidhuber says, of his PhD at the time, Sepp Hochreiter, who came up with long short-term memory, it falls naturally out of recurrent neural networks. And this was 20 years ago that we actually, that Sepp and Jürgen Schmidhuber came up with this, but they didn't have the compute power to really do anything with it. They didn't have the data to really do with it. So they're really quite happy about this now. But essentially, LSTM has dominated the field. Sepp is now head of bioinformatics at the University of Leeds, and his day job is now in the medical profession. He's doing a lot of work with pharmaceutical companies for drug discovery, targeted drug discovery, and really impactful work. Supercomputing, robots, and all the rest, basically they help us throughout our daily life, but this isn't just an image. This is poverty at work, and I have friends obviously in the work that I do in charity. The real impact here is that for people who don't have electricity, who don't get up in the morning and have a coffee, because first of all they've got to boil water and they've got just many more things that they have to concentrate on. But what they do have is they have mobile phones, and they can take some of the impact that deep learning is providing them, even if it's just saying hi to me on Facebook. You know, my friends in Kenya, they have that connection because of Facebook, which is essentially an entire deep learning backend. Google is purely deep learning now. So this kind of impact will affect millions and millions more that are about to join us all on the internet with via mobile technology. And they can reap some of the impact that deep learning is currently affording us. But, and I will be ending in just one more. What I want to talk about is where it will all lead. The phone in your hand already has superhuman powers. Superhuman powers of computation and memory, far better than us. The Wi-Fi codes that you gave it either yesterday or today gives it access to the world's information. Humanity will continue to make progress in hardware and software, but we should be thankful for the fact, the insight that we had to create the Future of Life Institute and Nick Bostrom at Oxford's Future of Humanity, so that we're considering this winner-takes-all strategy that artificial general intelligence could possibly have. If you imagine just for a second a computer built to be no more intelligent than, say, DeepMind's team, functioning on a digital timescale, it will run 1 million times faster than the minds combined over in King's Cross, which means that operating for just a week, that computer would perform 20,000 years worth of work. So for deep learning's true impact on modern life, who rolls the dice? I would ask the question, who decides what morals we code into an artificial general intelligence? How do we code empathy? I'm quoting Sam Harris here, a neuroscientist again, when I say that the only thing scarier than building an AGI is not building one, not understanding one. So on that point, I'm going to very cheekily end with the simple fact that we have our GTC coming up in April. If anybody can make it over to Silicon Valley, we would love to have you. And thank you very much.
Thank you, Alison.